let's do an example with simulation. So we said, like, okay, if you make this assumption that it's second order, even if it's higher order or if it's got zeros in it, it's only valid under certain conditions that we talked about in the last lecture. But even if we're feeling confident that this higher order system is going to approximately behave like a second order system, and we can say like settling time should be 4 over zeta omega n or whatever, our rise time should be this. Even if we check those assumptions and they're all true, we should simulate at the end to make sure that there was nothing funny going on, and also see how close we are, because we might be like 3-4% off. We might want to adjust. We're thinking about design. We're thinking about changing a parameter to make it fit certain criteria, like settling time criteria. So criterion. So we're going to want to look at the simulation at the end and say, okay, we need to maybe tweak something in our design to make it actually get. So maybe like we have a percent overshoot requirement of 10%, and it's actually 12% after we use the second order approximation. We might need to tweak something in our system to make it a little bit lower still. So let's do that in simulation. This is actually the best way to do the design process, to go through the design process. I'm going to kind of show you guys how to do that. So many control systems are not in the class of those that we have described analytically, first and second order systems without poles. In order to evaluate their transient performance, regardless of how well they are approximated by the analytic solutions from before, we will simulate their step responses. So that's what we'll do. We're going to use MATLAB to do it. I might eventually develop a Python version of this too, but for now, MATLAB is our major friend with this material. So anything to do with system dynamics and control systems, MATLAB has really nice tools for that. So I'll introduce you to a couple. So consider, for instance, a closed loop transfer function with closed loop. It doesn't need this second with transfer function. I changed that sentence. So we have a second order system, right? I say zeta is 0.3, so it's underdamped, and it's got 20 hertz natural frequency. Or 10 hertz natural frequency, I should say. And it's got a 0, but I didn't, so this 0 is Z. I wrote it kind of funny, right? Man, this is one thing on the exam that happened a lot. People forgot that this was supposed to be a 1, and this was supposed to be 1 over tau. Or no, tau times S. Tau S plus 1. So many people didn't do that. That surprised me. But in any case, this is the 0 here. And I want to explore what happens when we move this 0 around. So say this 0 is close to the poles, or it's like further out. So we're going to explore what happens to these transient performance characteristics when we move that 0 around. So this is actually a second order system. So if it had no 0, we would have exact analytic solutions for it. But since it has the 0, we know that that isn't quite true. Like those analytic solutions are only approximate, and they only are very valid in certain locations for this 0. So let's explore that. Clearly, for large negative values of z, the response should be approximately congruent with the exact analytic solutions of lecture 3.2. So if the 0 is way out to the left, we know it doesn't really affect things. So remember that the distance, the real part of this complex conjugate pair of poles, our dominant ones, I'll put them a little closer to the axis. This part here is negative zeta omega n. So it's 0.3 times 20 pi, which is 6 pi, right? So like 20 hertz. approximately. Well, not hertz, about 20. So we need our 0 to be like way out here, right? Like if we want it to be valid assumption. But if it's in here, we don't know what happens, right? All bets are off. We need to simulate it and see what happens. So, yeah. Specifically, the rise time will be described by figure 3.3 if the 0 is way out to the left. The peak time will be this expression we found, exact expression from lecture 3.2. The percent overshoot will be this, and the settling time will be that. So these are all the exact analytic solutions for a second order system without a 0. So we move that thing way out here, and we know those will be pretty good approximations. If they're at least 5 times further out. If it's at least 5 times further out. So let's compute these analytic values of the performance characteristics first. Like, so assuming that our 0 is going to be way out there, what should we see happen for the rise time, settling time, etc.? So in MATLAB, I define z for zeta to be 0.3, natural frequency to be 20 pi, the damped natural frequency to be omega n times the square root of 1 minus zeta squared. So just plug those in, plug and chug, right? The TR, the rise time analytic, you have to look it up from figure 3.3. Well, actually, I forgot to divide by omega n, right? Oh, man. Screwed up. Now it's going to be on the internet that I screwed up. Just this once. This is history right here. Okay. Good. TP, the peak time, is pi over omega d, the analytic expression. And I just plugged in these other analytic expressions. So 313, 314, I just plugged those in. And I didn't put semicolons so we could see the printout. So this is actually divided by omega n. And so let's do that calculation live. You guys want to do it live? Let's do it live. 1.39 divided by, our natural frequency was 20 times pi, right? So 0.0221. We'll call it. Okay, so we're going to come back to that. I clearly forgot to check this at the end. Okay, so there's our rise time, there's our peak time, there's our percent overshoot. These are things that would be true if there was no 0 exactly, okay? Now, let's define the transfer function object. So I'm going to do something a little bit, there's a very straightforward way to do it, and that's just to define one transfer function. But you can't define a transfer function object without picking some z value, some value for this 0 location. It has to be numeric in order to define this transfer function object in MATLAB. So I would have to pick it to be like 10, negative 10, or I guess it would be 10 or 20 or whatever. I have to pick a number, but I don't want to pick a number. I want to design this thing for potentially different values. I want to see what happens. So this is really common when we're doing design problems. So I wanted to teach you guys a way to do this. One way to do it is to define your script with, like, say, try 10 in it and run the script. And then, like, say, okay, this is the result. And then go back and change that value and run it again. That's a pretty good way to do it for a sort of one-off simple problem. But it's good to be able to explore sort of a range of values also in one shot. So that's what I'm going to teach you how to do. It's a little bit tricky, and I think that MATLAB is a little hard to deal with for this. But there is a way to do it, and so I wanted to show you a way to do it. So the first thing we do is we're going to say we want our 0 to be at negative zeta omega n which is, remember, the distance to the complex conjugate pole pair that we want to be dominant, right? I shouldn't say we want it to be dominant. In order for our approximations to be true, they should be dominant. Maybe our design doesn't require that they be dominant, so we'll just see. But we want to explore what happens when 0 is close and then when 0 is far away from them. So I'm going to multiply that. I'm going to define an array of different values. I want to do 1.5 times out, so clearly not very far away. So 50% further to the left isn't very far. We want it to be at least factor 5 for that approximation to hold true, that analytic approximation. So 1.5 is not very good. So we should see a pretty significant deviation with this value, the first one. Then 3, which is sort of an intermediate one, right? Like, it's not 5 times, but 3 times, it's not bad. And then 5, which is like our standard for saying this approximation should be pretty good, right? Okay. Then I just define this variable nz, the number of zeros that I'm going to try. And then I'm just going to do a little for loop. Well, first I have to initialize this model array. So there's this type of object in MATLAB. This is something that I really hate about MATLAB. Some of their data types are really weird and hard to initialize, including this thing called a model array. You can't put a system model, a TF object that you return, into a regular array because MATLAB arrays only take in numeric values, or symbolic values, but they don't take in these system, they call them model objects. So, but they do have this special thing called a model array that allows you to define an array of these models. It's not the same type of array as your typical MATLAB matrix, right? So you can't quite treat it that way. However, if you use this stack function, you can generate one with a dummy transfer function in it, which is just sort of weird, but as far as I can tell, the easiest way to do it. And then you're going to go through your loop and you're going to overwrite this first one, and you're going to also populate additional values in the array. So what this says is F, which is our model array. So this is going to be an array of system models, one for each value of 0, right? So we're going to get a 0 at each of these values. So or we're going to have a different 0 for each of these transfer functions. So we use the TF function, which defines a transfer function object. The TF function is the heart of this. So TF, if you open a parentheses, MATLAB will just pop up and it'll say, you need to put a numerator in and then a denominator in. And what it's looking for is an array of polynomial coefficients. It knows that you have a transfer function described like this, and it wants you to put in what the coefficients of s, s squared, etc. are into this array. So it like already knows what you want for the most part, but you just need to tell it what those coefficients are. So we put in the coefficients of the numerator, and then we put in the coefficients of the denominator, and we close it off, and that returns this transfer function object. And that's what we're going to put into this model array. So this is just the syntax for like all rows, all columns. It's a multi-dimensional weird thing, but this is just how you have to always refer to these model arrays. The first two indices, you just take the whole thing. All rows, all columns, and then this third index indicates which model you're talking about. So the first one we're going to say is omega n squared times, and then you've got negative 1 over ZA, the ith one. We're going to take the ith one because we're going to do the ith, we're going to assign to the ith model array the ith z value, the ith 0. Okay, so our negative 1.5 z omega n is going to be this first one. And that's the first coefficient of s. Second coefficient is 1. First coefficient in the denominator is the s squared coefficient, right? So that's 1. So our array is going to look like 1, comma, and then the next one's 2 zeta omega n. Oh, I forgot an s in there, didn't I? No square, just s. 2 zeta omega n, comma, omega n squared. So that's the array that we're going to define for the denominator. So that's what this is. Oh yeah. So the s squared had a coefficient of 1, the s had a coefficient of 2 zeta omega n, and then the s to the 0 coefficient is omega n squared. So now we've defined our transfer function for that value of a 0, and then we go through the loop again and we get the next 0 and the next 0. So now we're going to have this model array that has different models in it. So we can simulate different models by just looping through this if we want, which is exactly what we'll do. So for a step input, unit step input, and initial value y of 0 equals 0, let's simulate. So this is the standard step response that we simulate. 0 initial conditions, put a step in, and see how it responds. The step function would be the easiest way to solve for the step response. However, we choose the more general LSIM for demonstration purposes because in LSIM you can put in really any input you want. And so I wanted to show you guys, hey, this is, generally you can put in any input. So I create a time array. I go 0 to 0.3 seconds, which actually took a little, I simulated it to 1 second, and then I was like, oh no, 0.3 is better. I could have gotten more precise. It could have been like, oh, well, we use the theoretical settling time for that, but I just didn't. And I was like, I want 100 points. So lin-space, generate 100 points between 0 and 0.3. U is this so-called, I call them pure functions in MATLAB. What do they call them in MATLAB? Anonymous functions. Anonymous functions. You don't have to do a function file. So U is a function of t. And it's kind of weird, but what it does is it returns a vector of ones. So if t is 100 long, t is going to look like 0, 0 point, whatever it is, 0, 1, let's say, just for the sake of argument, etc. This u is going to look like 1, comma, 1, comma, the same, every time value has 1 in it. And that's how you define an input for a simulation in MATLAB. You define the input at every time step. So that's what I did. So u is now a function that's going to return that. So if I plug in TA into u, it's going to return this array of ones that size. So that was, and you could multiply this by a step input of 4 instead of 1. So it's kind of a nice little idiom. Once again, so this is one way to do it, but there are a lot of ways to do it. That's part of why programming is hard, right? Is that there's a lot of ways you could do each thing. This is one way that I hope I find really helpful. I hope you guys do too. So then I set the initial condition to be 0, and I initialize the time array, which I don't have to do. So if this is confusing to you, it's not that big of a deal. You can kind of skip it in MATLAB, but it is typically computationally more efficient to pre-allocate or initialize an array before you enter the values into it. So that it actually stays in one block of memory and it's not spread out throughout memory. the way that I do this is as I generate, so a lot of people use zeros to do that. They generate an array of zeros, the size that they want, and then they start putting values in. But zero is a legitimate number that I could be simulating, and I don't want to end up not knowing if the simulation worked or didn't work. So what I always do is I generate an array of ones, and I multiply it by nan. Nan is a special object in MATLAB that means not a number. And this will put a not a number in every single element of this YT array for me. So then when I go through and I simulate it and I write values to this array, it'll overwrite these nans. And when I get to the end, if I end up with an array that has nans in it, I'll be like, oh, this probably didn't get written to at any point. So that's easier to debug, I find. But that's just like my own little idiom. I don't know. If you find it useful, great. If you don't find it useful, don't need to use it. So what I do here, so I'm pre-allocating this array. So I'm saying that the rows here, I'm going to have NZ rows, which is the number of zeros I'm going to try out, which was 3, right? We're going to try out 3 different zeros. If I made this array like, 20 long, I could try out 20 different values of zeros. And actually, this code would just run it just fine. So you could do more values by just adding more to this array. So try to always write your code that you can, so you can do that, right? You can pivot easily. Because you never know when you're going to have, a mistake. I won't even call it a typo. A mistake in like this 4th line of your code. And then if you hard-coded things all the way through, then you got to go through and fix the whole thing. You guys have all done this on paper. I bet first in your statics class, when you guys screwed up one joint, summing the forces on it, and then like 3 pages of calculations went by, and then you realized that that was a mistake, and then you had to erase because that engineering paper is expensive. I've had this experience. I'm not sure if you guys had this experience. So that's one of the reasons why I don't write pages of calculations very much anymore. I typically use computers to do these things because I can change one thing up here and then everything else changes. Really nice. Like that. Okay, so where are we? We are here and we're about to do the simulation, right? So this is like the next big thing. So we define the transfer function TF. There was some programming stuff in between. And then now we're going to do the simulation. And the function we use is LSIM. We want to simulate what happens for each of these cases. So if the 0 is in this place, that place, or the other place, right? There's 3 different locations. So we're going to do a loop, one for each 0 value. And we're going to call LSIM. We're going to give it the model associated with the first 0 first, and then so the ith 0, right? So the way that you call it, once again, it's just sort of the way that MATLAB has these things set up. It's all rows, all columns, and then you take the ith system. And then you have to give it the input. So I want to give you our function that returns ones, the size of whatever the array is that I feed it, ones the size of TA. And then I want to give it TA with a time array that I want to return the simulation values to. And then I want to give it the initial condition. I forget, if you don't give it an initial condition, I think it'll assume it's 0. Not totally positive, but I like to just do it just to make sure I know what I'm doing. And then another thing to note is you don't have to give it a time array either. In fact, it ignores your time array for the actual simulation, but it just returns the time, it returns the simulation values at your time array points. So if you don't give it a time array, it'll actually return a time array that it calculated for you. I don't like that very much. It's not really my style. I like to roll my own, right? So I don't want MATLAB making this array for me. I don't know what size that array is going to be when it comes out. It makes me uncomfortable. So, oh my god. No, okay, at the end. It's just a meme. Okay, which is the most important thing. So this is the simulation that happens for each of these systems that we define, right? We simulate it, we assign it to the ith row, and then all of the columns, right? This thing returns a value of y for each value of time in the time array. So that's what we're populating here when we go through the loop. So like pretty straightforward, but I mean we're using all the stuff that you guys have learned in MATLAB, right? For loops, we're using special functions from the control toolbox. LSIM is from the control toolbox. Array construction, yeah. So the total solution is shown in figure 3, 4. So they all qualitatively look similar, right? Which doesn't surprise us. We change one parameter in a system that doesn't make it go unstable or something. We don't expect it to be hugely different, but it is significantly different in certain aspects, right? So when the 0 is at negative 28, which is pretty close to the negative zeta omega n, which is the pole location, right? So this blue line is when the 0 is pretty close to the poles, which means that our analytic approximations we don't trust in this case. So notice that it's like a significant overshoot, and the rise time is quite a bit shorter than if you have the 0 further out, right? It's the orange one gives you a something that's closer to the negative 94. When you go 5 times out, you get something that's looking like, so if I looked at this just eyeballing it, it's like 45% overshoot, because this gets up to about 1.45, I would estimate, at its peak. So I would say like just eyeballing it, 40% overshoot. Overshoot equals 40. So that would be, so like that's getting close to the analytic one. What was the analytic percent overshoot? 37. So this is with no 0 in there, 37%. So clearly though, when the 0 is way out there, when the 0 is pretty close, negative 28, the percent overshoot's like over 100%, right? It's like 130, 125%, which is way different than 37%. So you might say, great, but eyeballing it from these graphs sucks. We're doing programming. Can't we find a better way? Yes. Yes, we can. Glad you asked. This is what it goes. This is like how my brain works too. I just like have this conversation. Anyways, now this indicates that the 0 location definitely matters, and that the deviation is worse the closer the 0 gets to the poles. Quantifying the response characteristics is tedious visually, but MATLAB has a built-in tool that helps, step info. So if you're like, hey, what's the rise time? Well, I gotta go to 10% of the final 10% of the peak value, and the 90% of the peak value, and I gotta figure out what that time interval is. I'm like eyeballing a bunch of stuff, right? And it sucks. It's not very accurate. And if you have to do that for a bunch of different things and you're like iterating on it, it's not very convenient, right? So step info comes in. And what I did is I set this thing up in a loop. What you do with step info, the function, is you give it your step response, yt, and you give it your time array. So, and then what it does is it says, oh, okay, I'll calculate the all of these things. So it gives you an object in response that has like rise time, peak time, percent overshoot, settling time, and some other stuff too. Steady state value, like there are like several things that it'll give you. And you can select them out. This is an object that you can select things out with these expressions. So I'm assigning the result of step info in each time through the loop to an array of them, and then I'm taking the rise time and assigning that to an array, taking the peak time, assigning that to an array, and the overshoot, assigning that to an array, settling time, setting that to an array, and then I define the row name to be, I'm going to create a table of these, and then the 0 is going to be at whatever the 0 value is for that time through the loop. So this is this is something that would really help if you're going to do a big analysis with a bunch of different values and you want to see a table of what value corresponds to what. If you're doing a one-off calculation, you just call step info and then you just say like dot rise time, and then you look at what the rise time is. So one-off calculation, you don't need to do all this, but if you're doing a sort of thorough design, you're going to want to use something like this where you generate a table. And generating a table in MATLAB is, like everything in MATLAB, a bit of a pain in the ass to do. So I'll show you how to generate a table. Labeling the columns is the first thing I'm going to do. I'm going to put rise time in the first column. I'm going to put peak time in the second column, percent overshoot in the third column, settling time in the fourth column. I call this table function. I hand it column vectors for these 4 quantities, so rise, time, peak time, percent overshoot, settling time. So I do these primes there that do the transpose because they're all row vectors, and table will be like, what do you want me to do with these? So I have to put them in columns, and then they know. And then you give it variable names, which I said are these labels. And those are the column names. And then row names are these values here, so the 0 values. Okay, and it generates this nice, I just printed it out, I just didn't semicolon it. And it gives us this nice table, which says when the 0 is here, we get this rise time, this peak time, this overshoot. So like significant overshoot, 47% is what it calculated for the 0 5 times out, which is 37 was the analytic value. So it's still like not even perfect, right? It's just an okay approximation. It's not even a great approximation. If you moved it out further, it would get better. The settling time isn't significantly affected, and neither is the peak time. They're both about the same. The rise time is pretty significantly affected, though. So, anyways, these two functions, like TF, LSIM, and step info were the 3 main functions that we learned about in this lecture, and they're vastly helpful for doing design of a control system in MATLAB. We'll expand on that. Next week we're going to be digging quite a bit deeper into how moving things around in the S-plane affects these parameters. So, all right. See you on Friday.